Howdy and welcome back. We're going to begin with programming paradigms. So, what is a programming paradigm? Well, it's simply going to be a style of programming. Kind of the three major styles that are out there are going to be imperative programming, where the control flow is explicit, where commands show how the computation is going to take place explicitly. So, we're actually going through and defining the individual steps of each operation that we'd like to carry out within our applications. Contrast this with declarative programming, where control flow is implicit. Commands focus on getting results and not on how to obtain it. So, to date, what we've been doing in our C++ language has been imperative programming. We've been specifying the individual computations that are needed to arrive at some sort of result. For instance, if we wanted to find maybe every movie within a collection of movies, so a standard, let's assume it's a standard template library vector, at this point, what we do is specify the steps to perform that or find, say, all movies that are with a rating of maybe PG. We probably start out with maybe a range-based for loop. So for auto ampersand movie in movies, if movie's rating is PG, maybe we'd go ahead and collect that in another collection called PG movies or something of that nature. But we're actually specifying the individual steps to go from kind of this want to the end result. We're having to um, go ahead and consider each of the commands that would be involved in that sort of computation to take place. Now, declarative programming, we've seen kind of a declarative language already in this semester. When you think back to when we introduced databases, we introduced the SQL language, right? And we said we could perform different operations. So we covered how to create records, how to read records, update, destroy records, and all of that was just requests to the database engine. We could say select all records from maybe the movies table where the movie's rating is equal to PG. In this case, that command is focused on getting the result, and there's none of these. We're not going through and implementing different steps to actually uh, acquire that result. It's just we're simply asking for it, and we're given the result back without any sort of consideration as to what's happened in between. Again, now contrast that declarative implementation or at declarative solution versus the imperative solution where we actually had to walk through the collection, look at the individual ratings of the record, collect them into some sort of new collection, and then return that, maybe to the caller. Declarative, we just ask and we receive. Function programming, we can kind of think of declarative in some ways. It's going to have a control flow being expressed as a combination of functions, so we won't see any sort of iterative statements that we had when introducing our imperative um, programming style. So instead, conditional expressions and recursion will be used to perform computation. And we're going to get into some of the functional style programming later than this week that focuses on the idea of composing functions with functions. We'll get into what a higher order function is, what is considered a first class function, and how some languages support this while others may not. So the programming paradigms this semester, you've been introduced to, I guess, different styles of programming using the C++ language. If you think back to maybe the first week of class before we introduced functions, you were programming purely imperatively. You were using a series of statements to show the computer how to solve a problem, but you were writing long sequential code. You weren't creating any methods to kind of enhance the readability of that code. It was just, here's how you do things in C++. Let's work with our conditional statements. Let's work with our iterative statements. Let's introduce some collections. And now let's get into functions and different ways to pass arguments to its parameters. This kind of transition here, when we introduced functions, moved us from this purely imperative, almost I guess, script-like, if you will, code to procedural programming, where we were still doing imperative programming, specifying how each kind of step in a computation would take place, but we also introduced functions to kind of create maze in the uh, to create order in the maze of algorithms that were kind of just thrown together before we introduced functions. Finally, we began moving into object-oriented programming. So we began encapsulating program state, so different data, together with the behaviors that operate on that data. So kind of bundled together into different types of objects. We've also talked about recursive programming, solving problems by breaking them into smaller pieces. We didn't necessarily do this explicitly in this course or introduce it as such because you had seen it in CS 125. However, this was a recursive, this was a style of programming that you used in this course. We found it particularly intuitive when we were talking about different traversals of our binary search tree. And there are very many kind of other problems where a recursive solution might be more natural or easier to think about than its iterative counterpart. But remember, anything we can kind of do recursively for the most part. We can also have an iterative solution for that as well. But sometimes the actual solving of the problem might be more sensible to use a recursive programming approach. Another style that we saw here was generic programming, where we wrote code that worked for a variety of different types presented as arguments that meet specific semantic and semantic requirements. This was our function templates, where we could essentially leave open the types of the parameters, and as long as they supported the operations within the body of that function, we were able to use that definition with various types, and the compiler would actually instantiate that function template for various concrete types that were users of it. In addition to this, we introduced class templates, where we said, okay, here's a kind of cool way that we can leave open the types of objects that are maybe being housed within a particular class, or maybe interacting with its objects in some sort of way. We said that the compiler would go ahead and essentially instantiate our 4 concrete types from our class template to create different types of objects within our program. And remember, we said that like a stack of integers was a different type than, say, a stack of characters, and that the compiler actually would generate the definitions for those any sort of behaviors declared or even private member functions for each of those types. Because again, it was a template from which we could kind of do that find and replace process, where if there was a single type parameter t, when we instantiated the template for, say, int, all of those t's would be found and replaced with the concrete type int. And we saw how powerful this could be, particularly with a collection such as our, I guess we built up a pseudo vector, our vector int, which eventually was transformed recently into a class template, and we kind of saw the power of that. Though we did build up a singly linked list that could contain elements of all type t, for which the synaptic and semantic requirements were met. In addition to this, we talked about shared pointer, and we can go on and on, but we could see how generic programming could provide or be very useful for us in a wide variety of context. So with that, let's go ahead and move into this section called Beyond C++, and then we'll reflect on our progression in the course so far and consider where we're going.